Welcome to Variational Principles and Lagrange's equations. Today we are going to discuss a derivation of Lagrange's equations from Hamilton's principle. The idea now is that we want to study the variation of a line integral j depending on a functional f which contains several functions y and their derivatives of a given parameter x. And in the case of the variation, I am assuming that all of the varied functions behave in the way expressed here. So the functions of parameter x and an additional parameter alpha, which describes the parametric variation of these curves, is given by a function y of x and alpha equals 0, which corresponds to the correct path plus parameter alpha multiplying a function eta. So these are the solutions to be obtained, and the functions eta are independent functions vanishing at the endpoints and continuous through the second derivatives. The variation is expressed as was done previously, so I need to take a derivative of all of the functions contained within f by the parameter alpha, and then the second term here is treated just like we did previously in the one-dimensional case. So this thing is given by a total derivative with respect to x from this quantity, and from which we subtract the derivative applied to the factor containing f. And once again, in this case, so the derivative and the integral cancel out, and I need to evaluate this term between the endpoints. But the derivative of y with respect to alpha is just the function eta, which vanishes at the endpoints. So this term goes away, and I am left only with the second one. And as such, the variation of j is given by essentially a sum of integrals for each integral containing the variation of a given function y of index I and this coefficient. Now, because the functions y are independent, then their variations delta y are also independent through the independent eta I functions. As such, the variation of j is 0 if all coefficients vanish separately. And in this case, it is clear that these coefficients, which resemble what we would expect to be a Lagrange equation, become what are known the Euler-Lagrange differential equations. Their solutions represent curves for which the variation to 14 of the line integral vanishes. This is all which is really required for the discussions of classical mechanics that are to follow, but further generalizations of the variational calculus can include things such as higher order derivatives of the y functions contained in the functional f, or multiple parameters xj leading to multiple integrals and derivatives of yi with respect to xj, or even variable endpoints for the line integral. As a simple application, we can consider the shortest distance between 2 points in space. The line element is simply the Euclidean distance between the points, but this time we consider it in three-dimensional space, and then we can write the line integral as a two-dimensional functional depending on the parameter x. So this is the functional which interests us, and if we apply the Euler-Lagrange equations to each coordinate, it follows trivially that both y and z need to be linear functions in the parameter x, and as such, the shortest distance between 2 points in space is a straight line. Um, Furthermore, in order to obtain the Lagrange equations, it is enough to observe that the original action integral uh, presented in Hamilton's principle, which is the integral over time for the system's Lagrangian, is of the form of equation 214 with the following transformations. The parameter x becomes the time, the functions y are the generalized coordinates, and the functional f is the system's Lagrangian. Now, because the result 218 assumed independent variables, it means that the generalized coordinates are independent, and as such the constraints are holonomic. In that case, the Euler-Lagrange equations become the proper Lagrange equations, and this concludes our proof of them following from Hamilton's principle for monogenic systems with holonomic constraints. As an application of, or better said, an illustration of the more general principle, we can consider Lagrangians containing time derivatives of the generalized coordinates that are higher than the first order. And they are used to derive equations of motion for so-called Jerky mechanics, which finds application in chaos theory. So in order to study such systems, we will consider the more general variational principle where the line integral j is taken over a functional f depending on the function y, its first order and second order derivative with respect to a parameter x, and the varied paths are assumed to be given by parametric families both in y and in y dot, which involve the correct paths for the vanishing value of this parameter epsilon, plus the functions eta, which are independent, well-behaved, and vanishing at the origin, at the endpoints of the integration interval in both situations. So, expanding the line integral is straightforward. We immediately obtain the result here, and we need to work out this term and this term. We'll be applying the same idea that was already used in the previous demonstrations. So we know how to treat the first one. This is just the total derivative with respect to x of this quantity, from which we subtract the derivative applied only to this factor. And as for the second term, we do the same thing twice. So it's first the derivative with respect to x of the quantity here, from which we subtract this term, and then we apply the same trick again here, which is given by the following two terms here. And then it is clear that this term, and this term all vanish because they involve these derivatives which are 0 at the endpoints because the eta functions and their derivatives vanish there. And as such, the variation of j is given by the expansion here. So it's a sum of line integrals involving the variation of each function y and multiplied by a coefficient which looks like what would be the usual Euler-Lagrange equation for the function y, but we also have this additional term here. So the condition for the vanishing of the line integral, assuming that these are all independent functions and independent variations is that each of these coefficients vanishes separately. And then it is clear that if we were to discuss the action integral, involving the integral over time between two given moments uh, from the system's Lagrangian, assuming that this Lagrangian depends on the higher order derivatives of the generalized coordinates, then by identifying the parameter x with time and the functions y with the generalized coordinates q and the functional f with L, we immediately obtain from the previous result the proper Lagrange equations describing the dynamics of such a system where higher order derivatives of q are involved. As an illustration, we can consider the Lagrangian here, where the second term is something which clearly resembles an elastic potential energy for something like a harmonic system, but the first term is no longer a kinetic energy, but it's a product between Q and Q double dot. And if we work out the partial derivatives involved in this more general form of the Lagrange equations that was deduced here, what we obtain in a very straightforward way is simply the equation of motion of a simple harmonic oscillator of frequency omega given by the square root of k over m. Now we will discuss a couple of topics that will become relevant in future chapters in all sorts of situations. The first topic involves impulsive forces, which are instantaneous forces that are very large but act only for an infinitesimal amount of time, delta t, such that their impulse s is finite. So the impulse is defined as the integral of this very large force over a very small time interval, such that the result is finite. And then if you write the usual Lagrange equations in their more general form, so involving a Lagrangian which contains the kinetic term and the potential term from which conservative forces can be derived, and also generalized forces which are not derivable from potentials. We can then integrate this equation over the small time interval delta t during which an impulsive force would act. And then the right-hand side, denoted by Sj, is just, according to this definition, is the impulse of the generalized force Qj. And the first term here then is simply reduces to the partial derivatives of L between, taken as a difference between the final and initial moment, and the second term simply vanishes. So what we're describing here is the situation in which these very strong forces act so quickly that they change velocities or they change momenta that are involved in the system's dynamics, but they do not act for enough time to change coordinates. So the fact that coordinates do not change is represented by this derivative vanishing when taken under the integral. However, momenta do change as given by what survives out of this term when integrated, which is just the difference between the final and initial state. As another important topic, we will now suppose that we are describing systems where the kinetic and potential energy can be written as separable functions. That is, both of these are sums of functions involving only a given generalized coordinate or generalized velocity. So we don't have mixed terms in these two quantities. Then in that case, the Lagrangian is obviously given by the expression here, and we can immediately work out the Lagrange equation corresponding to a given generalized coordinate qj, and the result is the one here, which involves the derivative of the function Vj contained in the total potential with respect to Qj. This term involving the derivative of the function Fj with respect to Qj and the square of the generalized velocity Qj dot, and a term involving both the function Fj depending on Qj and the acceleration Qj double dot. And now the trick is to realize that formally I can write this acceleration as follows. This is the total time derivative of Qj dot, but I can multiply and divide this expression by the differential of Qj. And in doing so, I can write the expression here as a product between the generalized velocity Qj dot and the derivative of the generalized velocity Qj dot with respect to Qj. And then I can integrate this once again to obtain the expression here, 1 over 2 times the derivative with respect to Qj of Qj dot squared. And the reason why I'm doing this is because then if I take this expression all the way back here, then this whole result integrates immediately into what you see here. So in other words, the quantity in the brackets is a constant c, and then I can just solve the equation for Qj dot and integrate it. And the result is the one here. So this result just gives the time as an integral over the coordinate Qj from an expression containing both the f functions and the v functions, depending on Qj. And in principle, this is a result that can be inverted in order to furnish the generalized coordinate Qj as a function of time. And we will find applications for this, for example, in the study of the central force motion. And with this being said, in the following, we are going to discuss a few simple mechanical problems related to the minimization of action integrals. For the first application, we will consider a particle that is subjected to the potential v of x is equal with minus f times x, where f is a constant. The particle travels from x equals 0 to x equals a in a time interval t0. Assuming the motion of the particle to be expressed as given here, so a x as a function of time is a quadratic function, we are asked what are the values a, b, and c for which the action integral is minimized. So the action integral is given by the formula here. It's the integral from 0 to t0 from the system's Lagrangian. The Lagrangian itself is just the kinetic energy minus the potential, which is just plus f times x. And we know that in order for the action integral to be minimized, the Lagrangian must satisfy the Lagrange equation. So if we just work out the derivatives involved, we obtain immediately the equation of motion, which states that the acceleration in the x direction is just F divided by m. Now, we already know that the law is of the form written here, so then we can calculate the corresponding velocity and acceleration in terms of constants a, b, and c to obtain the results here. And then, knowing this and knowing this, it follows straight away that c is given by F over 2m. Furthermore, we know from the statement of the problem that at the initial moment x has to be equal to 0, but according to the law which we have proposed here, x must also be equal with a. So the result is that a must be equal to 0. And then we also know that at the time t0, x is equal with little a, and the general expression in terms of the functional form that we have proposed is the one given here, where we know who c is. So knowing who c is and knowing this, it follows that capital B is given by the expression here. Hopefully I did not get anything wrong. That's another problem. Suppose it is known experimentally that a particle fell a given distance y0 in a time t0, given by the square root of 2 times y0 over g, where g is a constant, and the times of fall for distances other than y0 are not known. Suppose that the Lagrangian is known, but instead of solving the problem, it is guessed that y must be of the following functional form. So a term which is linear in t and a term which is quadratic in t. If a and b are always adjusted so that the time to fall y0 is t0, show directly that the integral, that the action integral, is an extremum for real values of the coefficients only when a is equal with 0 and b is equal with g over 2. Well, since we have guessed that y is of this form, we can immediately calculate the corresponding velocity and acceleration, and the conclusion that is drawn immediately from these expressions is that a and b are both, in any case, they are both positive. Because if b were negative, I would end up in situations where the body would not fall, or if y is negative, I would be in a situation where the body first goes up and then starts to fall eventually. So these things don't really make any sense, and even assuming that we do not know the times of fall for other distances, but we know that the body in any case always falls, it means that these quantities are positive. Then in that case, we can, from these expressions, write the kinetic and potential energy immediately in terms of the body's mass, of the two constants a and b, and of the parameter d. And then we can immediately write the Lagrangian and calculate the action integral as the expression here. So you see that this is a sum involving 3 terms, and because we already know that these quantities are positive, 2 of these involve squares, and this involves their product. Again, since we're implicitly talking only about real quantities, it means that if we want the action integral to be a minimum, the only possibility is to have 2 of these terms vanishing, which would involve one of the 2 constants to be 0. The experimental fact, which is known, is this one. And for the corresponding time t0, our functional form gives the result here. So solving the equality between these two, we obtain the following relation between A and B, the expression given here. Now, we could assume that B is equal with 0, which would mean that A is equal with G over 2 times T0, but the problem is that if B equals 0, the acceleration vanishes. So again, if I would be in a situation where if I actually have an initial velocity which is negative, the body would never fall. So it would fall in any case, since the acceleration is 0. It would fall with a constant velocity, which doesn't really make any sense, assuming it's free fall. So this possibility doesn't really lead us anywhere, and the only possibility that works is the one involving that A is equal to 0, which implies that B is equal to G over 2, case in which the action integral has the value here. So notice that this value of the action integral is actually larger than this one, but this one corresponds to the correct law of motion, which is the one for accelerated motion with constant acceleration. And there is no other combination of constants that could work in this particular case. And finally, we are going to discuss a problem where we are considering a one-dimensional harmonic oscillator having the usual Lagrangian, and we are to assume that the law of motion is unknown, but we realize that it must be periodic, and as such it can be described by a Fourier series with t equals 0 chosen as a turning point, with omega the unknown frequency of the motion. So the general expression is the one here. It's a Fourier series uh, in the parameter j omega, and involving j omega, and the amplitudes aj for each of the periodic functions. This representation defines a many-parameter path for the system point in configuration space. Considering the action integral for 2 points t1 and t2 separated by the period capital T equal with 2 pi over omega, show that the action integral is an extremum for a non-vanishing x only if all coefficients vanish for j different to 1 and omega squared equal with k over m. So the dot here needs to vanish. And the solution is given as follows. So we know that x of t is given by the expression here, by this Fourier series. So x squared is simply a double sum over the indexes I and j. And given this expression, we can immediately calculate x dot as the formula here, and then x dot squared follows again as a double sum over I and j. Then knowing x squared and x dot squared, we can calculate the Lagrangian straight away, and we can calculate the action integral as per the expression presented here, which involves a double sum over integrals of this type. Now, remember that these integrals are always taken over a period of the motion. And what happens in that case, what you can check very easily, is that these integrals always vanish unless the indices I and j are equal, case in which each integral is equal with pi over omega. And then the immediate result is that the action integral is given by the sum here over the squared amplitudes of the motion and these coefficients. Now, the variation of the action integral, the variation of I, is given by the variation of these amplitudes according to the expression here. And we In order to find the correct path of motion, we impose that the variation vanishes. As such, if we expand the sum, the delta I is given by the formula here and has to be equal to 0. So it is then clear from this expression that A0 has to be equal with 0, and furthermore that all coefficients save for one of them must vanish. The particular coefficient which we restrict to be non-vanishing is for the one for j equals 1, and for that particular coefficient it will follow that if the coefficient is non-vanishing, then the parenthesis must be equal to 0 when as such omega squared is equal with k over m. Now, in summary, we have derived the Euler-Lagrange equations from Hamilton's principle and studied the simple application of the shortest distance between 2 points in space. We have derived Lagrange's equations for mechanical problems from Hamilton's principle in the usual and generalized forms. We have studied the behavior of the equations when handling impulsive forces and the conditions for solutions in terms of quadratures. We have studied various minimization problems for the action integral for simple mechanical problems, be it a case of constant force, free fall, or harmonic motion. In the following, we will generalize Hamilton's principle to systems subjected to constraints. That being said, I want to thank you very much for watching the video. I hope you found it worth your time, and I will catch you later. Goodbye.